So I think it's 5. Shall we begin, Jonaki?
Yes, sure.
Okay, fine. So let me welcome all in the meeting. It so happens we are not many today. I think it is the festival effect that is taking place probably. People are getting ready to enjoy the long weekend and festivals. So anyway, with that as a joke, let me welcome Dr. Jonaki Ghosh, an old friend and old supporter of technology in math education. Jonaki is a faculty member at the Department of Elementary Education, Lady Shri Ram College, University of Delhi, New Delhi. She teaches courses on mathematics education, and her primary areas of research interests are in the use of technology in mathematics instructions, professional development of mathematics teachers, and popularization of mathematics. She has published articles in proceedings of conferences as well as international journals and authored books for school students. She regularly delivers talks and conducts workshops in national and international conferences. And she has been doing it regularly in time since inception anyway. So thank you, Jonaki, for that. And she has set up Ramanujam Foundation for Initiative in Mathematics Education, which caters to professional development of mathematics teachers at all levels of school education. Our workshops focus on innovative practices in teaching mathematics through hands-on activities and technology, and emphasizing enhancing of content knowledge of teachers. She has helped to set up math labs in various schools in India. So with that short introduction, let me welcome Jonaki to today's talk. Okay, so Jonaki, please.
Thank you so much, Professor Rana, for having me here. It is always a pleasure. And I've been seeing how wonderfully Math Clinic has been getting sessions conducted by various speakers on various themes related to mathematics education. So I think that's really a wonderful effort. So I will share my screen now. Please give me a minute.
Please.
I hope it is visible.
Yeah, screen is visible. Your audio is clear.
Okay, thank you. So the title of this session is Technology-Enabled Explorations, a rich context for integrating computational thinking and mathematical thinking. Well, I guess people have been talking about this term for quite some time, and it has featured in some of the term of computational thinking, and it has featured in some of the policy documents as well. But what is it? And recently I became more interested in its linkages with mathematical thinking. So the outline of the talk is as such that first I will present a brief overview about computational thinking and highlight its connection with mathematical thinking. So CT and MT are computational thinking and mathematical thinking. But the larger part of this session will focus on how students of middle and secondary school did explorations of open-ended problems and engaged in both CT and MT. And I would like to end with, maybe some suggestions or some thoughts about implications for the curriculum. So one can't talk of computational thinking really without mentioning the name of Samuel Papert, who vividly talked way back in the 1960s, actually, vividly talked about children using computers as instruments for learning, for enhancing creativity and innovation. And actually, he was responsible perhaps for concretizing this term, computational thinking. And his book, Mindstorms, Children, Computers, and Powerful Ideas, is a wonderful book in which he gives many examples. And, he was founder of the Logo Programming and Turtle Geometry. And in that, he shows how mathematics is actually a natural playground for engaging in computational thinking. And basically, that did a lot of explain certain experiments where children were asked to design certain shapes using the turtle and so on. So this he was really the one, I think, who started off with computational thinking. And but in 2006, the term was suddenly popularized by an article by Jeanette M. Wing in ACM for Communications, and the title of it was also, which is a short article of about 3 pages, whose title itself is Computational Thinking, in which he said, computational thinking is a fundamental skill for everyone and not just for computer scientists. So she said it's like a way of thinking. And to reading, writing, and arithmetic, the 3 R's, we should add computational thinking to every child's analytical ability. So, what are the processes of computational thinking? Some of the key concepts, if you look up any website and you read about computational thinking, 4 processes are usually talked about: decomposition, pattern recognition, abstraction, and devising algorithms. But researchers have explored this little more in depth, and David Winthrop and his research team brought out a sort of a set of computational thinking skills, and said that the ability to deal with open-ended problems, dealing with complexity, representing ideas in computationally meaningful ways, breaking down problems into simpler ones, creating abstractions, and so on, generating algorithmic solutions, which are all an extension of what is there on the circle, are some of the computational thinking skills. And if we look at mathematical thinking, what is mathematical thinking? Perhaps these are mathematical habits of mind. Is there an echo or?
No, so I think somebody's mic is on probably.
Okay.
Yeah.
So the mathematical habits of mind. Is it okay now?
Yeah, fine.
Which entails, creating visualizations, making strategic guesses, engaging in systematic experimentation, looking for patterns, identifying invariances, making logical connections, and engaging in multiple paths of inquiry. So there is an overlap definitely between the two, that is computational thinking and mathematical thinking. And policy documents like the PISA 2021 mathematics framework has pointed out that the long-term trajectory of mathematical literacy should also encompass the synergistic and reciprocal relationship between mathematical and computational thinking. And in the National Education Policy 2020, there's a mention of it in linking it with mathematics, says that mathematics and computational thinking will be given increased emphasis throughout the school years, starting from the foundational stage. And it briefly talks about it, it's just a brief mention of computational thinking. So mathematical thinking skills and computational thinking practices are distinct and yet mutually supportive. But to bring it about, the challenge remains is that what kind of tasks should we do? Should students be exposed to, or should they explore, so that they can employ CT practices and also foster, which also foster mathematical thinking? Technology as dynamic geometry software, computer algebra system, and spreadsheets can play a significant role, perhaps if used properly, in mediating both CT and MT. And it is hard to put processes in two separate bins, because there are, as I said, many overlaps between CT and MT. But if we look at problem solving, recursion, modeling, and simulation, this could be part of both. CT further, if you talk about devising algorithms, that would probably come more under computational thinking and coding, whereas justifying solutions and proof come more under the purview of mathematical thinking. So I would like to now share a few tasks that were done by students. I usually start with fractals because these are done with younger children, and typically children of middle school also enjoy fractal based activities, and they are a good resource for generating both, encouraging both MT and CT. So in these tasks, students looked at explore geometrical factors such as the Serpentine triangle, Serpentine carpet, pot snowflake, and others, and also created their own fractals. Through these activities, they engaged in multiple representations. So they looked at the fractals pictorially, numerically, graphically, symbolically. And the use of technology was also there because you can't really visualize fractals. The fun of doing fractal activities is to visualize them, at least see some pictorial representations of initial stages. And GeoGebra, Mathematica, and Mathigon. So different age groups to use different software tools for visualizing these. But for numerical representation, spreadsheets such as Microsoft Excel were always the best option. The math concepts that these activities covered were, so fractals is not usually taught in the curriculum. So, but through these activities, they explored concepts of area, perimeter, geometric sequences, and further went ahead to things beyond the curriculum, like identifying self-similarity and computing fractal dimensions and so on. So we all know that fractals occur in nature. So whether it is certain kinds of leaves which have self-similar structure, in the sense that if you look at a smaller portion of the leaf, it's actually almost a replica of the whole leaf. Or if you look at the branching of trees, and if you look at a smaller portion of that, it kind of resembles the larger portion. And something like the cross section of a cauliflower, or the cauliflower itself, where if you look at a small portion and you magnify it, you would find that it almost resembles the whole cauliflower. So fractals exhibit self-similar patterns in progressively smaller scales. But fractals occur in nature, so that's a good enough reason to explore them. But to make it easy for students, for school students, perhaps geometrical fractals, as I mentioned earlier, like let's suppose the Serpentine carpet is a good example. It's a geometrical fractal which can be generated using a recursive process. So, so we start with initially we start with a square, let's say, and if you trisect, I'll try to draw it also if possible. So if you trisect the sides of the square and divide the square into 9 smaller squares and remove the center square. So it's like a cardboard piece, and if you cut out the center piece, what you will get is this. So you'll get this shape with the square hole. This is white portion as a hole. And you can see that there are, you can divide this part into these 8 smaller squares remain. And the same process is repeated on each of these smaller squares. So, you trisect them and divide them into 9 smaller squares and remove this and do it for each of them. And you would get this. And if you keep on doing it, as you see by stage 3 itself, it becomes fairly intricate and complex and beautiful also. So given such a pictorial representation, what kind of questions can be asked to students? So one could be, how many blue or shaded squares will there be at the next few stages? So can you predict the number of shaded squares at the next few stages? Also, can you find a rule for the number of shaded squares at any nth stage? So generalization. And if the shaded area at the nth, can you find the shaded area at the nth stage if the area at stage 0 is, let's say, at this stage is, let's say, 1 square unit? So area and number of squares are 2 attributes definitely with children, young children also can deliberate upon. And what happens as the number of stages grows indefinitely? So here n denotes the number of stages. So what happens when that grows indefinitely? So one good way is to get a tabular representation, get children to fill up a table where they, let's suppose T of n represents the number of blue squares. So they'll count the squares and find that, these are there's a multiplying factor of 8. So initially there's only 1 square, then there are 8 smaller copies of that. And Further, in the next stage, there will be 8 times 8, which is 64. And so we get, powers of 8. So at the nth stage, it will be 8 raised to the n. But if you look at the shaded area, so suppose at stage 0, it's 1 square unit, then since we are dividing this into 9 smaller squares and removing one, this will be 8 upon 9. And thereafter, the area will be powers of 8 upon 9. So the shaded area at the nth stage will also be 8 upon 9 raised to the n. So they again they already get 2 examples of geometric sequences, one which has a common ratio greater than 1 and one which has a common ratio less than 1. And apart from finding the explicit or the general rules, the recursive rules can also be encouraged. So if we say that T of n denotes the number of blue squares at the nth stage, then it is actually 8 times the number of blue squares at the previous stage, which is the n minus 1th stage. And similarly for the area. So in one go, one can look at the pictorial representation, the tabular representation, and also look at the recursive rules. So recursive rules are not that much, not really done at the middle school stage, but this seemed to be a good context to introduce students to the recursive rules. One can pull out a spreadsheet because it's very difficult to, see what the fractal looks like at higher stages, So, but if you want to know, if you want to explore numerically, that is possible. So one can, this is just a snapshot of a Excel sheet where the stage numbers are written. And the number of shaded squares is simply putting in the formula of the number of shaded squares and the shaded area helps children to see that the number of shaded squares is growing very quickly, whereas the shaded area is becoming less and less. And children use these terms like growing quickly and becoming less and less and so on. And then the graphical, they can, using Excel only, they can just quickly make graphical representations to show that shaded squares are increasing fast and the shaded area is going to getting less and less and perhaps approaching 0. So multiple representations are again reinforced. But if we come to the aspect of self-similarity, which is a real beautiful part of fractals and a part of their recursive structure. So let's say this is stage 3 of the Sierpinski carpet. And if I look at the portion inside this red circle, it is actually stage 2. But there are 8 copies of stage 2 sitting inside stage 3. So stage 3 has 8 copies of stage 2. Now, if I enlarge the stage 2, which looks like this, and I look at another small portion of this inside the circle, this is actually stage 1. So stage 2, and I can identify around this 8 copies of stage 1. So stage 2 has 8 copies of stage 1. Perhaps I'll just use my pen to just help you identify. So as I said, this is a stage 1, and there will be one here and one here. If I keep going this way, there will be 8 copies of stage 1 sitting inside stage 2. And if I enlarge this stage 1, it looks like this, and which has 8 squares, and each of this is a stage 0. So again, stage 1 has 8 copies of stage 0. Also, if I look at stage 3 and I look at a smaller portion, so this is actually stage 1. And I can really identify and count, there will be 64 copies of stage 1 sitting in stage 3. So again, there's a pattern there. So children started counting, they started identifying different stages and higher stages of the fractal, but they could not really go beyond stage 3 because getting a picture of anything beyond stage 3 is really difficult. So in general, stage n has 8 copies of stage n minus 1, 64 copies of stage n minus 2, and so on. So, if you, there are softwares which can at least draw the, up to stage 6 or 7. So the Mathematica command Venture Mesh N on Wolfram Cloud helps generate, slightly higher stages of this fractal. So, so this is a, Mathematica generated fractal. So I was just wondering if I can ask the audience to guess what stage this is. So if there are any responses, it would be nice to know. So which stage of the Sierpinski carpet is this? So if there are any responses on the chat box, then
yeah, you can put your answers in the chat box. We'll guide. So can you just repeat the question again so that
yes. The question is, this is a certain stage of the Sierpinski carpet generated using Mathematica. So which stage could it be? Like, is it like we just looked at stage 0, 1, and 2? So which stage can it be? So you'll be very interested to know what children said and how they. So typically, one would have to probably look at what is the smallest copy of the Serpentine carpet that I can see inside this. But when we asked the children, they simply said, one of them said that she said stage 4. And when we asked what is your logic, why it is actually stage 4. So I gave away the answer. But why is it? How did you guess? This child says that look, the biggest hole comes up, square hole comes up in stage 1. The next size will come up in stage 2. Then the next size in stage 3, and I can only see a very tiny white square hole. There are lots of them around. That should be stage 4. So very interesting where children actually surprise us by, highlighting their ways of thinking, very interesting ways of thinking. So I guess this is an easier way, though if this is stage 4, I can identify 8 copies of stage 3 sitting inside it. So for example, if I were to mark out this part, so this portion which I'm squaring out is actually a stage 3, and there are 8 such copies around it. But within this, I can see a stage 2, and there are 8 copies of stage 2, and so on. So one can see that recursive structure, but this child straight away looked at the sizes of the square holes and decided that what should be this thing. So children do surprise us, and they really take to fractals very well. And just to share some snapshots of some extensions done by students. So some children were very keen to, actually do a representation of the Serpentine carpet. And this child used cutting and folding. So she actually folded the glazed paper and made cutout square holes. So while stage 1 and stage 2 may still seem okay, but I thought stage 3 was particularly beautiful because she actually did it by hand and by cutting it out. And then, they started posing problems that, okay, if the initial stage is some area, then can you guess what the area will be at stage 3 and so on. Some other children decided to, just do a coloring work, and then they sort of, divided the initial square into 9 parts, which you anyway do for the Serpentine carpet, but said that what if we remove these 4 pieces, these yellow portions, and then repeat the same thing on the other black squares. So another very beautiful, intricate design came up, which is again a fractal design. It has self-similarity, but the geometric sequences that emerged, so they counted the black squares. So they came out to be powers of 5. So it is 1, 5, and then 25, because each of these black squares gives rise to 5 more, and each of these black squares gives rise to 5 more, and so on. So there were powers of 5 in terms of the number of squares. But then if they looked at the area, so if this is 1 square unit, then this is 5 upon 9, and then they arrived at powers of 5 upon 9. So different fractal pictures gave rise to different geometric sequences, and which was so class 11 students, when they can do a lot more with these sequences, and they anyway study the topic of geometric sequences. So it enlivens it for them. This is just a picture I found on the internet, but it's really beautiful. It is the world's largest Serpentine carpet. It's actually a basketball court, and it has been made. It is probably stage 5 if one looks carefully. But so it's children who have, children have been putting together pieces of squares and actually created this basketball court. So it's really beautiful and interesting as well. So I just thought I will share it. So fractals give rise to a lot of interesting explorations. Serpentine triangle is another simple and very interesting one, because it's just an equilateral triangle, and all you need to do is join the midpoints of the 3 sides and divide the triangle into 4 smaller triangles and remove this piece. So we get stage 1, and repeat the same thing on all the remaining. So in this triangle also, I will divide the triangle into 4 parts and remove the center piece, so that if I remove these, then I will reach stage 2. And we can again see that by the time you reach to stage 3 and 4, you get pretty intricate pattern. And this really fascinates children, the beauty of this itself. And then one can, of course, explore it in the same way as I showed you, but I'm not going to get into that. So what are the number of blue triangles at any given stage, and what is the shaded area, and so on. Another interesting thing that children like to explore, and they often ask, is why should we only focus on the colored triangles? What about the white portion, the holes? So is that also approaching something? And so students, slightly older students, start asking different kind of questions about the fractal and exploring it in different ways. But the reason I mentioned the Serpinski triangle is is to show its linkage with the chaos game. Now, the chaos game is an interesting game where, if you have a equilateral triangle, let's say we label the vertices of the triangle as, just for our convenience, as T. T stands for the top vertex, L stands for the left vertex, and R stands for the right vertex. And if we start at any point inside the triangle, so suppose I start with this blue point A, and I roll a dice. And the rule is that if you get a 1 or a 2 in the dice, then you move towards halfway towards the vertex T. If you get a 3 or 4, you move halfway towards the vertex L. And if you get 5 or 6, you move halfway towards the vertex R. So starting at any point inside the triangle, there is a equal probability, a probability of 1/3 of moving halfway towards any of the 3 vertices. But okay, so suppose in the first rule I get T. So I will take the distance between A and T and mark the midpoint. Now start with B and roll the dice again. And if I have to move towards L, then mark the point midway or midpoint of BL, and so on. So we keep on with them. As we roll the dice, we keep on getting newer points inside this triangle, inside or on the boundary of the triangle. But what does it do? So this is a GeoGebra snapshot. So after 200 iterations of this process, we can't really make out, but we can see a lot of these points inside the triangle. But after 1,000 iterations, we definitely get to see a Serpinski-like structure, Serpinski triangle-like structure. And why and how it is related to the Serpinski triangle is also an interesting exploration. So one of the ways of exploring the triangle is also that, suppose I look at stage 1 of the Serpinski triangle, there are 3 triangles. Let the top triangle be labeled as T, and the left as L, and the right one as R. And when these are further subdivided in the stage 2, then a sequence of 2 letters would be required, because the top of the top triangle will be TT, the left of the top triangle would be TL, and the right of the top triangle would be TR. And similarly for the others. So as you roll a dice, so suppose I start with a point somewhere inside the triangle, and in my first roll I get R. So I move halfway towards R. So that point will be lying inside the R triangle. Now in the next roll, if I get a T, suppose. So the next point, I'll be moving halfway towards the vertex T. So the next point will definitely lie inside the triangle TR. And it goes on. So at the next stage of the Serpinski triangle, we'll have a sequence of 3 letters, because there will be 27 small triangles and so on. So labeling these triangles, these are also called Serpinski triangle addresses. So there is an address or a label for each subtriangle of every stage of the Serpinski triangle. And then since there is a roll of a die involved, one can link it with probability as well. So we can say that, so one interesting game that children played was that, so they wanted to roll the dice, and the game says that you roll the dice, and you will obviously get 1, 2, 3, 4, 5, or 6, and those get translated to T, L, or R. So this is just a snapshot of the spreadsheet. So this row gives us the die rolls. So suppose we get 1, 5, 1, 6, 2, 3, and so on. Each of these numbers is translated to a T, L, or R, because 1 and 2 represent T, 3 and 4 represent L, and 4, 5, and 6 represent R. Once you get a sequence of these vertices, let us start looking at pairs. So the game says that, asks that how many, on an average, how many rolls of the dice are required for me to be able to identify all the 9 subtriangles of stage 2 of the Serpinski triangle. So which means that there are 9 subtriangles with these addresses. How many times should I roll the dice to be able to get all of these? So what it means is, suppose I have this sequence, and let me try and show you. So suppose the last two are T and T. So this last pair is TT. So I strike off TT because I've already got it. Next is RT. So I strike this off. Then there is TR. Remember that this is a randomized process. So this is TR. So I strike off that as well. Then RT has already been struck off, so I can't consider this. Then there is RR. So I strike off RR. RR is repeated, then there is LR and so on. So we keep going like this. So how many die rolls will be needed? So every child who did this got a different number of die rolls required to be able to get all these 9 subtriangles. And the average of that was computed. So they can play interesting games, but they also try to justify why is it so many. And so the chaos game and the Serpentine triangle can be linked very interestingly. Another interesting thing children suggested, and this is also a well-known thing, that we can modify the probabilities of moving towards a particular vertex. So in the initial case, we said 1 and 2 are T and 3 and 4 are L and 5 and 6 are R. But suppose I want to play around with that and I say 1, 2 and 3, let it be T. So if I get 1, 2 or 3, then we move halfway towards the vertex T. If it is 4 or 5, that we go to vertex L, and if it is 6, we go to vertex R. So now we are varying the probabilities of moving towards a particular vertex. And if you were to play the chaos game, what kind of structure would come up? Would we still get the Serpentine triangle-like structure? And it is interesting to get them to answer questions like, what is the probability of arriving at triangle R in one single roll? Now, if this is the rule of the game, then the probability of arriving inside R in one single roll would be only 1/6, because only one of the numbers out of 1 to 6 leads us to R. What is the probability of arriving at T, L, and R in 3 stages, and so on? This is stage 3. And this is the subtriangle TLR. So what is the probability of arriving inside this, and so on? So since each time you roll the dice, it is independent actually of the previous roll. So the probability of, let's say, arriving, so the probability of going towards T is half, towards L is 1/3, and towards R is 1/6. So for T, L, and R, the probability will be half into 1/3 into 1/6. And then asking a reverse question. Is there a particular subtriangle which has a probability of, let's say, 1/54 of arriving at in 4 rolls of the dice? So asking a reverse question. So probability and the game can be linked. So these kind of tasks really help in, in both computational and mathematical thinking. And of course, there are others. So there is this other concept of a dimension, because fractals are very complex objects. And if you keep zooming in on a fractal, you will keep getting to see the same structure again and again. So children are obviously, and we all are familiar with the fact that, a point is dimensionless, a line has dimension 1, a polygonal shape on the plane has dimension 2, and so on. But an interesting thing would be to explore dimension using some rule like this, where we say that, so for example, if I have a straight line, I know it is dimension 1, but if I divide it into 2 equal parts, then each part will be of length half unit. So in this case, A denotes the number of parts and S denotes the length of the smaller part, which is being repeated to form the whole part. And D, of course, represents the dimension. If I look at this case, then the number of pieces is 2. So if I substitute in this formula, now A is the number of pieces that we have divided the line into, which is 2. And so the value of S will be half because the length of each piece is half. So S is equal to half here. And if I substitute here, I'll get 2 is equal to 2 raised to the D. And of course, D is equal to 1 satisfies, and we know that line is of dimension 1. If I look at the cube, for example, there are 8 parts. If you think of this, when I divide it this way, there are 8 parts. The cube has been divided into 8 smaller cubes. So in this case, A is 8. So I can substitute A as 8. and the side length of each cube is half of the original length. So S will again be half. So we'll get 2 raised to the D is equal to 8, and of course D has to be 3. So this formula gets justified for our regular the integer dimensions. But if I look at the Sierpinski triangle and use the same thing, what happens? So if I look at, let's say, stage 1, this is stage 1 of the Sierpinski triangle, which has 3 parts to it, because actually this in the center part is a whole, so it is not there actually. So there are 3 parts. So A has to be 3 in the same formula, but the length of each part of each triangle is half of the original length. So S is half. So inserting in this formula, I get 3 is equal to 2 raised to the D. So D here becomes log 3 upon log 2, which is something close to 1.585 and so on. Similarly, but this is constant across stages. So if you look at stage 2, now there are 9 parts. So A is 9, and each of these is now 1/4 of the original, because this is divided into 2 equal parts in this stage. And again, we arrive at the same. So a dimension lying between 1 and 2, that is something difficult to fathom. But there is, of course, when you study more about fractals and complexity, this idea will be used. But children find it fascinating that they also need to use logs in this case, and the whole process is sort of interesting for slightly older students. So what is the CTMT integration in this? So if you look at processes in such fractal activities, if you look at processes of recursion, generalization, modeling, and we look at the aspect of understanding fractal dimension, perhaps there's a mathematical aspect as well as a computational aspect. So finding recursive rules, expressing attributes of the nth stage in terms of the previous stage, or working out a geometric sequences arriving from different attributes of the fractal, calculating the probabilities of successive iterates in the case of the chaos game, and interpreting and visualizing the concept of dimension. These may be attributed to the mathematical aspect. But looking at specific copies of certain stages within certain stages and building higher stages from previous stages could be brought under computational aspect. And simulating the attributes on a spreadsheet, or simulating the die rolls in the case of the chaos game could be considered as could require computational thinking. So it is not that we need to force ourselves to look at the two as segregate these in 2 separate columns or something, but it would be useful to see and think about which aspect of mathematical thinking is being highlighted or emphasized through these activities, and which aspect of computational thinking is also being, and there of course might be overlaps. For example, exploring the problem using multiple representations, numerically, graphically, and symbolically, would well come under both aspects. So these fractal activities, as I said, are popular with children of all age groups. And now I'm coming to another problem, which is probably might be popular with slightly older children, because I tried it with only grade 11, and I'm sure that many others would also find it interesting, but it requires the concept of probability. So let us see what the spaghetti problem says. In some of you might already be familiar with it. So there is let us say that there is a spaghetti stick, and we are able to break it randomly into 3 equal parts. So the stick is broken into 3 smaller parts. And what is the probability that these 3 pieces will form a triangle? So let's say this is a stick, and there's a cut break here and there's a break here. And let us say that this break is of length, this piece is of length x, this is of y, and the whole stick is of length L. So the last piece is L minus x minus y. So these 3 parts, when will they form a triangle? So clearly they will form a triangle if the sum of any 2 of these is strictly greater than the third. So let us say if x plus y, using the triangle inequality, so if x plus y is strictly greater than this piece, or if x plus this is strictly greater than this, or another case where y plus this is strictly greater than x. So this leads us to some inequations. So let me quickly write that down. So if I work on this, I will get that x plus y is strictly less than L by 2. If I simplify this here, I will get y, x plus y is strictly greater than L by 2. Here I will get y is strictly less than L by 2. And here I will get x is, y cancels, x is strictly less than L by 2. And what are x and y? X and y are the lengths of the pieces. So clearly both x and y should lie between 0 and L. It could be that x is this whole thing also. So all possible values of x and y must lie between 0 and L, because L is the length of the stick. So if I plot these, so every time I break a spaghetti stick into 3 parts, there will be an x and a y. And if I plot that, it will be a point on this in the first quadrant, because of course x and y have to be greater than or equal to 0. I've already said that here. So every time you break a stick, there is a point. So the entire sample space, if I keep breaking many sticks, the entire sample space will be included in this bigger triangle. And this line is x plus y equal to L. I hope the idea is clear. Now, if I look at this line, x plus y is greater than L by 2. First, I plot the line, but x plus y strictly greater than L by 2 would mean that the region lies. So I'm looking at the common region to all these inequations. And this is something students do already in class 11. Of course, it should be on this side of the line x plus y. And since x is less than L by 2, so it will be on this side. And since y is less than L by 2, it will be below the line. So the common feasible region is this. And all the ordered pairs lying in this region will represent those cases where a triangle will be formed. But if it is here, here, or here, then the triangle will not be formed. So if I break lots of sticks and this entire big triangle gets filled up with lots of points, then the area of this triangle, the probability of a triangle being formed is the area of this triangle upon the area of the bigger triangle. So let us see what is the area of the bigger triangle, because the length, it's a right angle triangle, so half base into height. So L square upon 2 is the area of this big triangle. And this smaller triangle is L by 2 into L by 2 into half, so it's L square by 8. And that leads to 1 upon 4. So the theoretical probability that a randomly broken spaghetti stick will form a triangle is actually 1 upon 4. But so when children were given access to, different children explored this problem in different ways. Now, some children started saying that can we consider the 3 lengths to be x, y, and z of the 3 parts? But then if you are bringing in another variable z, then we come to the realm of 3 dimensions. And so let's say that, of course, x plus y plus z is equal to L, but this equation itself represents a plane. So if I take the intersection of this plane in the first octant, because in the first octant, x, y, and z have to be greater than or equal to 0. These are lengths of the pieces. So we need to see what is the intersection of this plane within the first octant. Which part of the plane is in the first octant. And then we have to come to these inequations, because the triangle inequality tells us that either x plus y should be greater than z, or x plus z be greater than y, or y plus z be greater than x. So the next stage was to first put equal to signs and draw these planes first, represent these planes, and then see the intersection of these planes with this one. And it would be difficult to even think of visualizing this problem in 3D at all, had it not been for, let me see if I can show you the GeoGebra file. I hope this file works, because it's a 3D representation of the same. Is it visible? Okay, so
yeah.
Yep.
Unfortunately, I'm not. Okay, right. So let's see this. You can see the algebra view on the left-hand side. I'm sorry for this zoom bar, which is bothering me. Anyway, so this is the three-dimensional axis, and the pink triangle is actually the plane x plus y plus z equal to 4. In this case, let's say L is 4 units. So this blue plane that you can see is actually x plus y plus z equal to 4. But the pink triangle represents the intersection of this plane in the part of this plane in the first octant. Okay, so that's the first thing. Then what we do is we look at the plane, let's say x plus y minus z equal to 0. And see the intersection of this plane with the pink triangular plane, which is this line. Both these planes intersect in a line. So I'm going to hide the first plane. The second plane was x minus y equal to z plus z equal to 0, which is this plane, and its line of intersection is this one. And the third plane was minus x plus y plus z equal to 0, which is somewhere here. And the intersection of that line of intersection is this. So I'm hiding the planes just for clarity. But these are the lines of intersection. And if you look at the inequations, the inner portion, the common feasible region will be in the inner portion. So this is an equilateral triangle divided into 4 equal parts, and all the points, all the parts which will form triangles, all the x, y, z values which will form triangles will actually lie here. So it is exactly 1/4 of the. So we can see this. So this was kind of a 3D visualization which was brought on, and students could then get to see that what happens if, if you introduce the variable z, because they just said it they didn't think of it so deeply that it would lead to such an interesting figure in 3D, but they kind of said, okay, we would like to have 3 different lengths for the three different variables to represent the 3 different pieces. So I'll just close the. So not only that, now if you wanted, those who wanted to simulate this problem on Excel, so how to simulate this problem on a spreadsheet? Okay, so this is the same, sorry, I just skipped this. Yeah. So let's see that again, we come back to the stick, and the 3 parts are A, B, and C, right? Now, when you're simulating the problem, I would need 2 random numbers, x, and let's say the L is 100 units in this case. This length of the stick is 100 units. I generate 2 random numbers, x and y. Now, x, whatever is the value of x, can be the length of the first piece, which is A. Whatever, what will be the length of piece B? So it will be the second random number minus this piece. And finally, what will be the length of piece C? That will be 100 units minus y, or 100 units minus A plus B. So it's very simple to visualize, think of what would be the 3 lengths if we get 2 random numbers between 0 and 100. So if the simple conditional statements can actually help us to randomly create the values of A, B, and C. But how do we check whether the values of A, B, and C will lead to a triangle or not? Well, since the length L, the length of the stick is 100 units, if the maximum value of these 3 pieces is less than 50, then a triangle will be formed, else a triangle will not be formed. So using this if condition with the maximum command, we got this, right? So let me show you quickly, if I can, the Excel sheet, which I hope I can show you that. Yes. Okay. So, sorry. So what you see on this, I hope the Excel sheet is visible.
Yeah.
Okay. So what we see here is a serial number column, which means that each row represents 1 spaghetti stick. So x and y are the 2 random numbers I just talked about. So for example, and A, B, C are the lengths of the 3 parts. And then finally in this column, we will check whether these 3 parts actually form a triangle or not. So let's say x is 25, the first random number, and y is 79. So A has to be 25, A has to be the smaller of these 2. B has to be the difference of these 2. And C has to be the difference of basically 100 minus the sum of these 2 pieces or whatever. So 100 minus 7. For example, in this case, A is 25, B is 79 minus 25, which is 54, and C is 100 minus 79. So it's very easy to put those conditions here and get the three pieces. Now the maximum of these values of these among these three is more than 50. So it doesn't form a triangle. So another conditional statement to check that. Now, why is this useful? Because if I screw, I can't actually keep breaking spaghetti sticks and checking. So I have simulated it on the sheet, and there are 100 simulations. It's like breaking 100 sticks. And each time you tap on the sheet, the commands, the new set of 100 sticks get simulated, and the probability is worked out here. So it is showing 0.25, but it will always not be 0.25. So suppose I tap again, I get 0.26. And if I tap again, I may get 0.24. So each time the empirical probability will be around maybe close to 0.25, but maybe quite far away also. So, but I can easily increase the number of simulations. I can quickly make it 1,000 simulations instead of 100. And then I would probably get a better approximation to the probability. So some children who wanted to extend the problem immediately asked, okay, but what will happen if we have 4 pieces? If the stick breaks into 4 pieces, then what will happen? Will it form a quadrilateral? The next step. And of course, that led to the question that what if there were, n pieces, and will n pieces form a n-sided polygon? So children wanted to, these are older students, these are, as I said, class 11 students, and these questions were popping up in their mind. And so some students focused on the n equal to 4 case, and they actually did a simulation of that. So instead of A, B, C parts of the stick, they now have A, B, C, D. And they found that the probability is coming close to half. So theoretically, then they tried to prove it. Is it really half? So if you actually, it's true, if you break a spaghetti stick into 4 parts, we can prove that the probability that these form a quadrilateral is half. And then others tried to generalize this. This is a purely a proof in probability, and that is, if there are n pieces, then I don't have time to go through the proof. It's a really simple and wonderful proof. But 1 minus n upon 2 raised to the n minus 1 is the probability for the generalized case, that whether the n pieces of the spaghetti stick will form an n-sided polygon or not. So again, if you look at processes, visualizing the problem or solving the problem or generalizing the problem, these were probably the 3 main aspects of this particular problem. So applying the triangle inequality to model the problem and then arrive at relevant inequations, or graphing the inequations and finding the common feasible region, what we did in the very first step, computing the theoretical probability or extending the problem to n pieces, all this require mathematical thinking. But modifying the problem for simulating it on a spreadsheet or creating a GeoGebra model, or extending the simulation to larger number of pieces would entail computational thinking. So I would say this is simulation problem and there are many other such problems which we can do with students to really engage them in both aspects of mathematical and computational thinking. Another topic which I'll quickly breeze through because I do want to finish on time is that of cellular automata. And so what is a cellular automata? Cellular automata is, it develops on a grid of cells in discrete time steps. The state of a cell in the 2-dimensional automata can be either dead or alive. So what basically it says is that there is a 2-dimensional grid. Some cells are black, some are white. So the black ones are live cells and the white ones are dead cells. And suppose this is the situation at time t equal to 0. At time t equal to 1, the configuration of these cells will be different depending on certain rules. But to apply those rules, we need to define some basic things like what is the neighborhood of a cell. So there are 2 kinds of neighborhoods. One is the von Neumann neighborhood, where in a given cell, we look at the top, the one above, one below, and the left and right. And then there's the Moore neighborhood, which comprises the 8 squares surrounding the center cell. So these are the two kinds of neighborhoods. But this is a very simple idea that, based on certain rules, this configuration has to change. Now, one of the most interesting things that students can and should explore is Conway's game of life, which has very simple 4 simple rules. And pictorially, I have taken them from the internet. That one of the rules says that, okay, there is a grid. The first, at time t equal to 0, let's say the blue cell is a live cell. And you have to consider all the 8 cells to be the neighbor cells. So if there's only one live cell in its neighborhood, then in the next iteration, this particular cell will die. So it will no longer exist. Another rule says that if there is a dead cell, that means, let's say that this particular cell is a dead cell and it has 3 live neighbors. So if any dead cell with exactly 3 live neighbors will become alive in the next iteration as if by reproduction. So here this cell dies due to lack of resources because in its neighborhood there is only one live cell. Here this dead cell comes alive because of reproduction. If a live cell, the blue cell is a live cell, if the live cell has more than 3 live neighbors, then it will die in the next step because of overcrowding, too much resources. And another rule says that, if the live cell has 2 or 3 live neighbors, then it will live on to the next generation. So these are the 4 simple rules. And if you apply these to any initial configuration on the blank, suppose there's a blank 2-dimensional grid, and you apply this into any initial configuration, what happens to that initial configuration? Okay, so let me just, sorry. So for example, and interestingly, the configurations have been given names. So for example, suppose you start with this as your initial condition. That means this is the initial configuration of cells. And you apply Conway's rules, these 4 rules which I just showed you. Then this will not change. It will remain unchanged from one time step to another. Well, this has a particular name called the beehive. Then there are those, like if you start with 3 of these squares, 3 cells, live cells, and apply the rules, it will go to this, and then it will keep coming back to this and this. It will keep oscillating between these two, and these 2 states, and this is called a blinker. But there are those interesting ones like spaceships which tend to glide over the screen. I don't know if I may take this opportunity to just, if possible, show you. There is a very nice site which can be used. Are you able to see?
Yeah.
Okay. So I was just telling you, so suppose, let's say the initial configuration is just these 3. And I start applying the rules of game of life. It will just keep oscillating between these 2 states. But I'll reset this. But suppose I take something like this kind of an initial condition, and I apply those same 4 rules. That is, because this game is programmed to do that. It tends to glide through the grid, and these kind of automata have been referred to as spaceships or whatever. So students, even if they don't know too much of coding or programming, sorry, I'll just stop this, they can actually explore using such sites. They can explore the game of life. But I just want to quickly share with you what one group of students, school students, class 11 students did. So what they did is they used the idea of 2D cellular. This is a two-dimensional cellular automata. They applied this idea to an evacuation plan. So every school has an evacuation plan in times of a crisis. So they tried to think what kind of movement rules can be devised. So what they thought is that suppose there's a room from which people have to be evacuated. So they think of the floor of the room as a 2-dimensional grid. So if a person is standing at a particular position, then that cell is occupied. And if there is nobody standing, then that's blank. So, in fact, the work has been published at right angles. Uh, so the reference is given at the bottom. So the rules posed by them were, so they devised these rules, again, inspired by the game of life. So they said a person can only move one cell at a time. So imagine that there is a room and a person can move only one cell at a time and can only move to the defined neighbor cells. Logically, a person would want to take the shortest route to the exit. So he will move to his neighbor cells, which is closest to the exit. But if an obstacle is present, then he will move to the next closest to the exit and so on. A person cannot move in a direction opposite to the exit. Obviously, if people are trying to rush out, then everybody is moving towards the exit of that particular room or hall. And if there's a conflict between two people for one particular cell, then the one closer to the exit will prevail. So these were some of the rules. Actually, they tried different kinds of rules, but they came up with this particular set of rules which they thought would work well. So if you are interested, do go through the article as I mentioned. But here it is that there is this grid. Suppose this is the room, and this orange thing represents the exit, and these are the positions of people at time t equal to 0. Applying those four rules of the previous slide, the next time step they will move here, and at the next time step, it is moving closer and closer to the exit because they have to depart from it. But ultimately, the programming by the students was done using Python because these students were the computer science students of class 11 and 12, and they were learning Python, and some of them were quite familiar with it. So they devised a simulation model, where they created many such things like they were thinking of the corridor in terms of the school floor, which has a corridor and classrooms. So, for example, they thought of equal sized room with equal number of people. How much time will it take for them to quickly depart to this exit? Or, they looked at three rooms of different sizes with different exit locations. And then there was a case where there were different sized rooms with different number of people. So basically, they considered various kinds of movements. And what would be the time, what would be the most effective evacuation plan would be that which would take the least time to evacuate the people. So it was, I'm only showing you a tip of the iceberg of the work done by students, but what I'm trying to say is simple ideas can actually lead to very interesting explorations. And since time is up, I think I'll sort of skip this slide and come to the closing and say that these kind of projects, when you take feedback from students, they have excellent feedback. Students own their projects, as if it is it's like their work, and so they feel very they have a sense of ownership towards it. They're proud of their project which they do. Technology, of course, plays a very critical role. Most often, it plays a role of an amplifier because students work more effectively. The tedious computations are outsourced to the tool, whatever tool is being used, and they focus more on reasoning, on developing insights. It also plays a role of a reorganizer in the sense that, not every project would have the same sequence because the problems are open-ended. But while working through the problems, they will get access to higher level concepts. Meaningful tasks are posed, outcomes are not always predefined, or answers are not always arrived at. But when they do arrive at certain answers, then there's a sense of suspense and many aha moments. But students ask a lot of questions. What if I do this? What if I want to try that? So multiple paths of inquiry is reinforced. And of course, if they get opportunity to present their work in fairs and competitions and even publish in some journals, that itself is a great achievement for students. So implications for the curriculum. So mathematics as a core school subject provides many contexts for integrating computational thinking. It's not that computational thinking should only be integrated in mathematics. It is a skill which is to be integrated in almost every subject domain. But because mathematics is like a natural playground, as Samuel Papert believed, inclusion of mathematical modeling and applications needs to be more brought into the school curriculum, but discrete math must be introduced at an earlier stage in the school curriculum. As students work through these projects over the years, I've noticed that, they engage in very interesting, very important processes which elicit both CT and MT. So like, selecting between representations, creating new ones, simplifying or generalizing problems, making conjectures, generating new questions for exploration. So when the spaghetti problem was given to them, honestly, I never thought that the student would really want to look at what happens in the general case, because these were only class 11 students. But automatically the question came to mind that if there are three pieces, then there can be four or even five. What happens in those cases? So there was a lot of engagement. What you saw was in a very quick snapshot I tried to describe, but it spanned out over quite some time, and it required them to uh, spend a lot of thinking time on this. I'm not sure if the titles are visible, but this says Computational Mathematics Lab. So I've always felt that, if technology anyway has to be a part, technology in the form of digital tools like dynamic geometry software or computer algebra systems or spreadsheets or even advanced calculators. If used properly, these can play a significant role in mediating both CT and MT. So setting up of computational mathematics labs. So what are these? I mean, this can well be done only through, even in the online mode. So initially mathematics and computer science teachers can work together with students and projects, because mathematics teachers may not have all the coding skills required, and computer science teachers may not have deeper knowledge of mathematics related to the problem, but together they can work, and they can work on exploratory and interdisciplinary projects. And this can well be outside the purview of the curriculum. What is to stop us from setting up these labs in schools where children, those who are interested, come and then they do work on these activities? Of course, the teachers also have to be interested, and they also have to invest that kind of time. But in the long run, I believe this is really worthwhile. Inquiry-based learning approach, I mean, I don't want to use any particular names or frameworks, but I do feel that in every project, students should engage with these problems and do inquiry at their level of competence. So not every child may be comfortable with coding, but the problem should be such that she or he can explore that problem even without coding to a sufficient degree of complexity. So choice of the problems is very critical. Teacher training, of course, will be important, but teachers and students have to be co-learners. So as I said, initially to start with, mathematics teachers can provide the mathematical knowledge, and the computer science teachers provide the knowledge of coding. And other teachers can be brought into this computational mathematics lab to identify problems in other subject domains which require solutions. And at the end, I would just like to quote from Cellular Papers from Mindstorms. It says that before computers, there were very few good points of contact between what is most fundamental and engaging in mathematics and anything firmly planted in everyday life. But the computer, according to him, is a mathematics-speaking being. In the midst of everyday life of the home, school, and the workplace, is able to provide such links. And the challenge in education is to find ways to exploit them. One of the ways is to definitely try and think of interesting ways to integrate these two kinds of thinking, and hopefully give students a wonderful experience of both learning mathematics and also developing computational thinking skills. So with this, I will end my presentation. Thank you for the patient listening.
Thank you, Jonaki. I think we can ask the audience if they want to ask questions, because chat box has no question as such.
Okay.
But probably
should I stop sharing then?
Yeah, please stop sharing.
Yeah.
And
thank you.
If you would like to comment on some idea that Jonaki has shared, or you would like to seek some clarification or anything regarding the talk today, please unmute your mic and say your name and share your thoughts. We'll be happy to listen.
Yes, that would be really nice, because
yeah, Professor Ramanujam is here.
But I can wait for others. But...
Yeah, please. We are honored to have you again.
Yeah. Thanks. It is, as always, a wonderful and stimulating talk, Jonaki. Thank you very much. I had one question, which is not really about doing this with children, but about these projects which of these have analytical solutions and how do we compare them? Like I was thinking that when you were presenting the chaos game, I was just thinking of it as a ternary tree, which is infinitely branching. And then I'm summing paths, right? And summing subtrees. So I can set up convergent sequences and set up sums and calculate. And that would be an analytical solution as opposed to, but I don't expect class 11 children to do anything of that kind. If they do, it's great. But just to understand the difference between, these as experiments and explorations, perhaps leading to analytical solutions, or certain cases where I can see also, like, cellular automata, I do not see analytical solutions at all. I think these things have to be simulated and computational. So is there some categorization of these things somewhere that would be useful?
Well, I have not delved that deeply into it, but I think, yes, what you just mentioned in the case of the chaos game, for example, I think we should encourage class 11 and 12 students to do those analytical explorations also. But in terms of, but when if there are students who are more inclined towards coding, and you want to give them a somewhat mathematical problem, then probably this. So very often they come up with the topics themselves, and sometimes they are very. So this cellular automata thing was kind of came from the students themselves, that they wanted to work on this, but they had not. They had heard of something called the game of life, so the lot of the exploration was done by themselves itself. But yes, I feel that it is not enough to do an exploration, but one has to cull out the mathematics and bring out the trajectory through which we can lead to analytical solutions. But I have not really seen a categorization of such problems, and I am yet to find. Recently, in fact, I read an article by David Winthrop, in which he writes about a simple exploration on the lattice, on the grid, and how middle school children, they just explore areas of shape, what we call a geoboard actually. So, and he talks about how through those tasks that were posed to them, they were supposed to find the areas of irregular figures and they were supposed to find a formula for the area of irregular figures using points lying on the lattice and so on. So how were the children scaffolded into doing so? And they sort of highlight which aspect is mathematical and computational and so on. But I have not read anything on slightly levels which are slightly higher, because when you access literature on computational thinking and its connection with mathematical thinking, people talk about STEM projects and what was done, but I've not seen anything which discuss the mathematical and computational aspect of it in detail. But I would really like to, because this area has interested me. But I'm sorry, I don't think I've answered your question. But I think that it is important to not leave explorations only as explorations, but to show students the deep mathematics that underlies those explorations. That I do believe in.
But let me just add to the Ramanujan's question, and probably I feel in that Sierpinski's triangle and those problems, I think there are some analytical results, but this is purely my guess. By now, people should have explored those things, and given, for example, where it may depend on the probability distribution that with which the things move.
Right.
So, Ramanujan, if you have some known result in that direction, that will be good, because that will support that mathematical thinking, computational thinking, which may lead to conjectures and lead to some results which are probably already known, can be proved probably mathematically. So I don't know.
Right. In fact, when we talk about one stage 0 to stage 1, let's say, of the Sierpinski triangle, we can link it with transformations also, matrix transformations, which lead to scaling down and scaling up and so on. Right. So there are the mathematics that I have seen a little bit as fairly complex, not complex for undergraduate students, but I think it would be a little complex for school students. Even the idea of this self-similarity dimension and all, and how do you really make students understand if there is a dimensional value of 1.5 something, but what does it mean in physical terms? So one needs to delve into these ideas as well. But only in terms of, these class 11 students had great fun exploring the topic of geometric sequences using fractals, because every fractal construction leads to such sequences. Now they say, well, as n tends to infinity, what happens? Does, like in the chord snowflake, we see that the area approaches a fixed value. And suddenly, they say, oh, but we had studied that S infinity, that formula A upon 1 minus R, so that we can see it physically happening. So some such visualization and some such concepts are, but it needs some much more deliberation as to which topics to take, which tasks to sort of get into. And for engaging students, I think.
Sure. Anybody else from the audience would like to add a comment, ask a question, discuss some idea? Professor Agarkar, I saw you joining. Would you like to say something? Add on to? I think this is whatever you may call it. You may call it project-based learning, inquiry-based learning, open-ended questions, mathematical thinking, computational thinking. The idea is how we can sort of excite students and bring out the potential in them. So that is what is important. And I think we are given enough thought, enough food for our thoughts, that we can bring in simple looking problems which are amenable to students, but which lead to some real deep solutions later on. So in case there are no more questions, I would, if there anybody, last call for questions, please. Comments, queries, and before you leave, please fill up your feedback form. That is important for us to continue doing this activity. So with that, let me thank Jonaki once again for accepting to be on this platform. She is always ready to accept such challenges on any platform. So
thank you, sir. Thank you for having me. And it's always wonderful. Learning would be mine, but I really hope people from the audience can share. We can, think more deeply about these kind of problems and what should we really do? Because even in online mode, can we think of some such, what I mean, is an idea of a computational mathematics lab, is it really possible?
Yeah.
So I really want your suggestions, thoughts, and you can.
And I think two things that you said were very important. Discrete mathematics and statistics are the two components of curriculum, even up to 10+2, which are the weakest.
Yes.
We don't spend time, we don't introduce these things early in our curriculum. And they play an important role in many applications. So somehow, I don't know, I have been also trying, like you, to tell curriculum planners and other focus groups to include something of that at the early stage, so that our students can see. You can see that once exposed, even at 11th standard, if they are exposed to these ideas, they can do wonders. And they can bring out results which are new and publishable in that sense. So that is one. And second is this: without the help of a teacher, it is impossible to do this kind of a thing. I think teacher plays a very important role. Teacher, I don't mean a school teacher. It is a facilitator. It could be anybody who can help them channelize their energy and way of thinking, model them so that they, and that again, I have been requesting, trying that our B.Ed programs, which are vanilla programs, should turn into something more useful. At least some parts of technology training should also go in there. So with that, I think, thanks for joining. And
thank you very much. Thanks a lot.
Your talk will promote computational and mathematical thinking among the audience and the teachers. Thank you very much.
Thank you so much. Thank you. Thanks a lot. Bye-bye.
Bye. Take care.
Thank you.
And have a happy Diwali vacation.
Same to everyone and the audience.
Thank you.
Happy Diwali.
Yeah, happy Diwali. Yeah.
Happy
Bye. Thank
Diwali.
you.
Yeah. Stay safe.
Hi and bye, Sonia.
Yeah, hi and bye.
We'll catch up.
Very interesting. Thank you so much. Yeah. Bye.
Thanks a lot. Bye-bye.